All right, so let's consider now just the units that we've been looking at. So in general, what is the unit of measure for our derivative f prime? If we have some function f, and we calculate its derivative, what would the units of measure be for that derivative f prime? Well, they're related to the units that we're using for our function f and for our input x. So it turns out the unit of measure for f prime is the unit of measure for function f divided by the unit of measure for input x. And a lot of times the way we read this division here, this quotient, we read that line as per. So some of the examples we looked at the population of the US. So in one example, so we had this function f of t, which gave the population of the US in millions of people t years after the beginning of 1800. And so for that example, what did we see? Well, the units for the original function f, were millions of people in the US. T, what were the units for t? Well, t was measured in years after 1800, but years nonetheless. And so then f prime, what would be the units of measure for f prime? Well, it would be millions of people per year. Or millions of people, you could have like almost like a division sign here, millions of people per year. So that would be the units for f prime in this case. We also looked at the example for national debt. So we had this function d of t, which described the national debt of the United States at time t. And in that example, we had a table of function values, and the units on d were billions of dollars. T, in that case, also represented years. And then d prime, this, what would be the units for d prime? Well, this would be billions of dollars per year. Or if you wanted to, you could have a little kind of division symbol here. But a lot of times we would, because it's more of a word problem, we would say billions of dollars per year. That's how we would write our units here. All right. Now, we've also looked at cases involving velocity and acceleration. Well, mostly velocity. Let's actually talk a little bit about acceleration here. So for the case of a moving object, we have this function s of t, which gives the height or location, the position function, of an object that's moving in a straight line. So for this little discussion, let's say s of t is the height in meters of a ball that's moving in a straight line. So maybe we have this ball, we throw it straight up into the sky. And so s of t is measuring the height of that ball in meters. So in this case, what would be the units for our velocity? So we've seen the velocity of this object that's moving in a straight line is just the derivative of the position function. So the units of our position function here are meters. A lot of times we abbreviate that m. What are the units for t, our input? What are the units for t here? Well, seconds. So it's measuring time. And a lot of times the way we abbreviate seconds is with just an s. And so what would be the units for our velocity function? You probably already know. But it's good to kind of talk about this. So the units for our velocity function would be the same as our units for our derivative of our position function, because they're actually those two functions are the same. So what would be the units for the derivative here? Well, it would be the units for s divided by the units for t. So it would be meters per second. Or we could write that as meters per second with the abbreviations. So that would be our units in this little example for the velocity of this moving object. Now, it turns out that the second derivative of our position function, the second derivative, s double prime, also has a physical significance, and it turns out that it's the acceleration. So if we do the second derivative of our position function, well, that's just the derivative of velocity. And so the derivative of the velocity function is acceleration. So what acceleration really does is it measures how fast the velocity is changing, whether your moving object is accelerating, so the velocity is increasing, or, well, has a positive acceleration, so the velocity is increasing, or does your moving object have a negative acceleration where the velocity is decreasing? And so what would be the units for acceleration based on the information we know here? So we start with the units for velocity. In this case, meters per second. Which we're also abbreviating like that. Then we also look at what's the actual variable for the acceleration, or for v, and the unit or the variable here is t. So again, we're using t, which had units seconds. And so for acceleration, which is the same thing as the first derivative of our velocity function, what we do is we take the units for v and we divide by the units of t. So the units for acceleration are going to be meters per second per second. I'm going to run out of room. Let's see. It's going to be close. Meters per second per second. Oh, that's close. You get it. Meters per second per second. Or another way to say that is you can say it like this, or probably better, meters per second squared. It's another way to say it. Probably the more standard version here. So if our position function is measured in meters, time is measured in seconds, that means velocity is measured in meters per second, and acceleration then is meters per second, or meters per second squared. All right, so just a little discussion about units there, just to give some more context about what the derivative is really doing. So for instance, in velocity, it's really measuring, the change in our position relative to the change in time, so meters per second. And for, say, the population, the derivative was measuring how much our population was changing per year. So the growth of our population divided by time. All right. So in the next lesson, we're going to be looking at we're going to develop some derivative rules. So we've seen how to calculate the limit definition of derivative. We've looked at a lot of different interpretations. We've seen how this all relates to difference quotients and limits. And now we want to kind of develop some machinery for calculating derivatives quickly. And that's what we're going to look at in the next lesson. So we'll see you there. Bye-bye.